In this lesson, we'll be looking at how we use logarithms to solve exponential equations and how to solve equations involving logarithms. So, first and most exciting, there are sort of three different kinds of equations we're going to be looking at. So we have our types of equations where we may want to use exponents or logarithms to solve, okay? So the first one we get is exponent. Type 1 will be exponent with a variable. Type 2, we're going to have a log equals a log with the same base. And type 3 is going to be log equals a number. And so each of these is going to have a different technique for how we're going to solve them. And we're going to look at one example of each type. So example 1. Let's say we want to solve an exponential with a variable equation. So something simple like even 3 to the x equals 7. We haven't actually been able to solve this before. So something where it's like 3 to some power is equal to not 9, not 81, not something that is actually a whole number power, or even a fractional power like radical 3. We want to know when it's equal to 7, what power you would have to raise 3 to get 7. So what we do in this case is we take the log of both sides, and notice we don't put a base here. So I'm actually going to take the log base 10 of both sides. And the reason is log base 10 is a logarithm that I can find on my calculator. You won't be able to find it if you're just using a regular phone calculator. You have to make sure you are using the scientific version of that calculator. So you may have to turn it sideways in order to get your friend the log. So once we get it to a log of both sides, one of the things that you may notice is that we can actually use our power rule for logarithms to bring the exponent down. So we can rewrite this as x times log 3 equals log 7, which is great. Now I can isolate the x by dividing both sides by log 3. And so I get x equals log 7 over log 3. Now this may not look any simpler than 3 to the x equals 7. In fact, it may look more complicated, but we can now get a decimal approximation by taking log of 7 and then dividing our answer by log 3. And when we do that, the answer we get is approximately 1.771. So if you raise 3 to the 1.77124, it goes on and on. But if you raise 3 to that power, you will get 7. Okay. So what about equations involving logarithms? So let's say we have an equation like this. So we have log base 3 of x plus 5 equals log base 3 of 2x minus 1. So if those two things are equal, if we have a log and the base is the same, we can actually just take away the log. So this means in order for the log of two things to be equal, we know, so if log A equals log B, that implies that A equals B. So we're going to use that rule here. So we have that x plus 5 equals 2x minus 1. We can do that because the base is the same. So I'm going to subtract x from both sides and add 1 to both sides. So that's going to give me x equals 6. Okay, so one of the things that we need to do is we do need to check that our answer doesn't make anything inside a log negative or 0, because we can't take a logarithm of negatives or 0. So checking is actually not an optional piece. So you must check solutions, because as much as it looks like the same thing, does not exist, does not equal does not exist. They both just don't exist, and therefore the equation is not a valid equation, because you can't say that because things don't exist, they are equal to each other. So we're going to go ahead and just plug in log base 3 of 6 plus 5 is log base 3 of 11. That's okay. And on the other side, log base 3 of 2 times 6 minus 1 is also log base 3 of 11. So the number inside is 11. It's positive, so that equation works out just fine. Okay, let us look at a third example. Okay, and this is going to be the trickier type of problem. So let's say we have log base 2 of x plus 1 equals log base 2 of 3x minus 5 and then plus 2. So that plus 2 is going to throw us off a little bit. So first thing we want to do is we have logs the same base. We want to get all of our logs on one side. So we're going to subtract log base 2 of 3x minus 5 minus log base 2 of 3x minus 5. We're going to subtract that from both sides. Okay, so what we get is log base 2 of x plus 1 minus log base 2 of 3x minus 5 equals 2. So you might notice now is we're subtracting outside of logarithms with the same bases, so we can actually use our quotient rule for logarithms to simplify this, to make it one term. So we get log base 2 of x plus 1 over 3x minus 5 equals 2. So now what we want to do here is we've got this equal to a number. So we're going to try to rewrite this in exponential form, because with exponential form, we are going to actually have the 2 here and the 2 here are both going to be numbers, and that's going to be equal to a variable expression. So our base is 2. That's the base of the exponent. Okay, so for these type, we're going to rewrite in exponential form. And so our goal in the simplifying for this type of equation, where we can't get it to be just a log equals another log, is to get it down to a single logarithm on one side and a number on the other side. So this is equal to, our 2 comes over here to be the exponent, and that's equal to our x plus 1 over 3x minus 5. So we get 4 equals x plus 1 over 3x minus 5. Noting that x cannot be 5/3, we're going to multiply both sides by 3x minus 5. So that gives us 12x minus 20 equals x plus 1. Multiplying here by 3x minus 5, for those of you who don't like the algebraic steps skipped quite so much. And there we go, expanding brackets. So now we're going to subtract and add to both sides. We get 11x equals 21. And dividing both sides, we get x equals 21 over 11. Now, I don't want to actually go through and try to calculate what that log base 2 of all that stuff is, but I do need to check to make sure that x is not going to give me a negative inside any of my logarithms. So let's see, we have log base 2, and that goes back all the way to my original equation. So x plus 1, so 21/11 plus 1 is going to be greater than 0. That's okay. And 3 times 21 over 11 minus 5, is that going to be greater than 0? Well, 5 would be 55 over 11, so this is 63 over 11 minus 55 over 11, and that is going to be greater than 0, so we're okay there as well. So that all will work out. But we do have to be careful, because if we ended up with a negative inside the logarithm, we wouldn't actually be able to use that solution.